Hello, my friends. This is your friend Brian, and I've decided that in addition to the chapter, I will also solve a few exercises for you to like understand the chapter better. So this is the part one of the selected exercises. There will be two parts. So this is the first part. So let's begin with some of the standard exercises of this book. Now, the first question is, a box contains three marbles, one red, one green, and one blue. So you can see that there are this thing, one red, one green, and one blue marble. Three marbles you can see there are. Consider an experiment that consists of taking one marble from the box, then replacing it in the box and drawing a second marble from the box. What is the sample space? So first of all, like if you are uh, there is one marble, means initially how many marbles are there in the box? There are three marbles, RGB, three marbles. Now if you are taking one, it can be any of them, and after that you are replacing it again. So you are replacing it, and that's in the second turn again you have the option for choosing RGB. So uh, there, note that there is a replace, we are replacing here, we are replacing it here. That is why we have this thing. So what is the sample space? One, they have asked. Sample space will be like this, RGB, RGB. RGB will be, one outcome will be RR, both of the marbles are red. Second will be RG, then there will be RB, then there will be GR, then there will be GG, then there will be GB, then there will be BR, BG, and finally BB. So there are nine, the sample space will have nine outcomes. Uh, if at all times each marble in the box is equally likely to be selected, what is the probability of each point in the sample space? What is the probability of getting this thing? Like if there is equal probability, then obviously for each point like this red, we will have this uh, 1 by 9, because everything is equally likely to happen. Then for red green we will have 1 by 9. Then there is another green red. Now say suppose somebody asks you like what is the chance that one will be red and the other will be green, so both of this will be uh, available, then there will be 2 by 9. But for the individual event RG or GR, if the like if the that thing, what is it called, if the, means if the placement matters, like from the first it should be green and from the second it should be red, then it will be 1 by 9. But if the order does not matter, then it will be 2 by 9, because there are 2 by 9 outcomes. Then for red there will be only 1 by 9, and like that. So uh, this is a very simple question. It tests the basic fundamentals. Now let's go to the next question. Aha. The question is that repeat exercise 1 when the second marble is drawn without replacing the first marble. So now the question is this thing, RGB. Now say suppose if you take red, then the second one will be GB. So now the probability for selecting this will be obviously 1 by 3. The probability for selecting any of this will be 1 by 2, right? Means in this particular case. So what will be the sample space? Sample space will be uh, you get RG, you get RB, you get like, if you take RG, then there will be like this, RG, RB, then there will be GR, GB, then there will be BR, BR, and BG, like this. So the sample space will be 6. And the probability of an event happening, like, notice that there is no red red, no blue blue, no green green. That is because, like, if we are taking it out, there are only 3 balls. If we are taking one out, then obviously it's not going to repeat. So that is why we have 6 sample spaces. And once again, what are the outcomes of these things happening? The chance of getting red is 1 by 3, 1 by 3. The chance of getting green is half, so it will be 1 by 6. Similarly, everything will be 1 by 6. All of this will individually will be 1 by 6. And if somebody has chance of getting one green, one red, then there will be this one, then there will be this one. So ultimately there are like means without, if the order does not matter, then there will be 1 by 3, and otherwise there will be 1 by 6. Now let's go to the next question. A coin is to be tossed until a head appears twice in a row. What is the sample space for this experiment? If the coin is fair, what is the probability that it will tossed exactly 4 times? So now let's see that a coin is to be tossed until a head appears twice in a row. Like, what is the sample space for the experiment? So basically, uh, if a coin is tossed, what is the probability that it will be head? It is half. So the it is given that two should be continuously head. So this will be like, we can get it in direct HH. We will get 1 by 4 chance of this happening. Then we will get this thing, uh, tail. First one is tail, then we will get head head, then we will get the probability for this happening is 1 by 8, because half into half into half. Then probability for getting uh, 2 tails and 2 heads is equal to 1 by 16, and tail tail head head, it will be 1 by 32. Means basically there it will be an infinite sample space, because like uh, it can happen that infinite times there are t and at the end there are 2h. That can also happen, so the sample space is infinite. Now the question is, what is the probability that it will be tossed exactly 4 times? So to toss exactly 4 times, what are the chances for this to happen? uh, it can be either, means 4 times means last two will must be head. Now the first two can be tail, the first can be head, the second can be tail, third and fourth will be head. Other than that, is anything possible? Head, head, tail, head. Obviously, no, this is not satisfying what we want. So, since this is not satisfying, then other than that, what can we try? Triple H and then H. Obviously not, because there are like, if there are two H, then we will stop. So these are the only outcomes that it will happen. Now what are the chances for this happening? The chances for this happening is obviously half into half into half into half, means 1 by 16. Then this will be also 1 by 16. So the probability that it will stop at this will be 1 by 16 plus 1 by 16. That is to 1 by 8. There will be exact, for 4 tosses the probability is 1 by 8. Now what is the probability that it will be tossed exactly? Now let's move to, so in this question we have been asked that argue that E is equal to EF union EFC. If I write it in mathematical notation, it will become like this: intersection F union of E F complement. F complement, I'm more comfortable writing it like this, like F complement rather than FC. So basically this is what they have asked in the first part. Now let's address it part by part. E intersection we know that F complement basically means sample space minus F. So this can be written like this: E intersection F union E intersection of S minus F. Alright, now if we write this, it becomes E intersection F union E intersection sample space minus E intersection F. Now we know that intersection of E intersection S will be E itself, because if we draw it like this is the diagram, this is E intersection and this is the whole sample space. The intersection of this part will be the sample space E intersection S, and if we do the intersection F, this will be the intersection F, and E intersection F complement will be this part, left side of E. Now if we break it, it becomes like this: E intersection F union E E intersection S minus E intersection F. So this part actually, this part is like union is basically like summation. So you can do it like this: E intersection F plus this thing E intersection S is E. I will write it in the last part. Uh, this union minus this E intersection F. So this part would get cancelled out, and ultimately we would be left with E intersect the complete E. Now if you ask me logically how is it happening, like this, and it is given that this part and this part are making a union. So obviously their union will be this thing, the complete E itself. So this is the first part. Now coming to the second part of the question, let me clear up things. Second part of the question says that you have to prove that E union F is equal to E union F and E complement, intersection of E complement. Similar to that, just roles reversed. So let me just clear it up, and I will touch it very soon. So here it is. Now argue that E union F is equal to E union F intersection E complement. We can write it as E union F intersection of 1 minus E. Here is the diagram for this. E union F, both of this. F intersection E complement is this part. F intersection E complement is this part, and E is this part. So let's do this. What we get is it won't be 1, it will be S. So what we will get is E union F intersection S minus uh, F intersection E. So that is basically E union of uh, F minus F intersection E, which is basically the right hand part of this part. So we can write it like this. Uh, so if we do a complement, it will become like E plus F minus F intersection E. Now we know that E plus F is equal to E means we know that E plus F is equal to E union F plus F intersection E, because if we take this part, this, if we do individual addition of these two circles, this section which is common here will be added twice. But if we do a union, uh, so we will, what we will get is this plus addition this part. So that's why this is what we are getting is this part, so equals to E union F. This part is also proved. Now going to the next question. Assume that each child who is born is equally likely to be a boy or a girl. If a family has two children, what is the probability that both are girls, given that the eldest is a girl, at least one is a girl? Good question. Now let us see at the sample space. Sample space is like this: probability of, like, equally likely, so 50% chance female, uh, male, female, male. Left one is the first one, FF, FM, MF, MM. So it is given that the first part is given that the eldest is a girl. What are the chances eldest is a girl? This one and this one. So both are girls. What is, so what is the uh, F eldest intersection FF is equal to FF, like this is the only intersection. Now the what is the total what is the chance that it is means the eldest is a girl, that is 50% chance, means a half. So basically we get is, what we get is 1 by 4 by half. 1 by 4 is this chance of getting FF in total sample space, is equal to half. Chances that both are girls, given that eldest is a girl, is half. Now for the second question, at least one is a girl. What are the chances? It is given that at least one is a girl. So in this case, in this case, and in this case, the chances are 3 by 4 that at least one is a girl. And uh, what is the chance that both are girls? Now both are girls is 1 by 4. So 1 by 4 by 3 by 4 is equal to 1/3. If we know that at least one is a girl, uh, the chances that both are girls is 1/3. And if we know that only if we know that the eldest is a girl, then the chances are half. So this is how it goes, and we will be continuing it in the next series. This is so far for this one. Thank you and have a nice day, and uh, keep in touch with me.